So let us start finding the field components. The field components are nothing but E theta and H phi. So our next aim is to find out the field components from the already found vector magnetic potential. Now how to relate the vector magnetic potential in the and the field component? We have studied that B is equal to del cross A, and we know that B is equal to mu into H. So therefore we can write mu into H is equal to del cross A, and this is over the angle phi. So this is mu of H phi is equal to del cross A oriented over our angle of phi along the z axis. Now we are going to actually find what is mu into H phi. So as per the definition of the spherical coordinate system, we know this is 1 by r square sine theta. Determinant of the three components are AR, R A theta, R sine theta, A phi, and then it is dou by dou R, dou by dou theta, dou by dou phi, and then it is the field, the magnitude of the vector magnetic potential. So it is AR, R into A theta, R sine theta into A phi. So this is R. So it is R square. We will divide it by R square, and 1 sine theta component. So this is sine theta. So we will divide it by 1 by R square sine theta. Because AR, A theta, A phi are unit vectors, so it has to be 1. So we will usually compensate by dividing it by 1 by R square sine theta. So now this is going to be equal to 1 by R square sine theta. Now if you see, this matrix has three terms AR, A theta and A phi. But our magnetic field is oriented only in the phi axis, which means I will not be considering these two axes when we find the required magnetic field. We will only find the value of this phi component. So taking this term alone, it is R sine theta into, so if you close this and this, it is dou by dou R of R A theta minus dou by dou theta of AR. Once again, AR is just the magnitude term. It is very small when you compare to the field. So this term will be neglected and this will be taken as 0. So this is going to be, we can cancel out this R and R square, sine theta and sine theta. So this is 1 by R, and the left out terms are dou by dou R of R into A theta. So this can be simplified as, let me scroll down. So we are writing mu into H phi is equal to, it is 1 by R dou by dou R of R into, the value of A theta is given as AZ into sine theta. It is minus AZ into sine theta, taking the axis into consideration, where AZ is the component which is oriented along the Z axis, and sine theta is because our waveform takes the sinusoidal wavefront. So we can simplify these terms. This is differentiation with respect to R. So we can bring the other components forward. So I am going to write this as mu into H phi is equal to, I will bring this minus sine theta forward. So this is minus sine theta divided by R, dou by dou R of, we have this R as such because it is partial differentiation with respect to R, and we already found what is AZ, which is our vector magnetic potential. So we'll substitute that here. So it is mu Im into e power minus j beta r divided by 2 pi beta into r cos of pi by 2 cos theta divided by sine square theta. So let us try to cancel out the possible terms. So we can cancel this r and r which is present here. So I'm going to find H phi, which is your magnetic field component. So I will have H phi here. I'll bring this mu to the left hand side. So this becomes minus sine theta divided by mu into r. We are differentiating with respect to r. So we will have the r components alone inside. Let us try to bring all other components outside. So it is mu Im divided by 2 pi beta cos pi by 2 cos theta divided by sine square theta, and dou by dou r of, the r term is e power minus j beta r. Now let us perform the differentiation. So this becomes h phi is equal to minus sine theta by mu r, mu im divided by 2 pi beta, cos of pi by 2 cos theta divided by sine square theta, and differentiating this we will be getting this as e power minus j beta r into r becomes 1 minus j beta. Now cancel out the possible terms once again. So the terms that can be cancelled are, here 1 sin theta can be cancelled. Here mu can get cancelled. Check out for any other terms. This beta can get cancelled. And I think that's all. You've cancelled out all the terms. Now this is just the magnitude of your, this is your magnetic field value. So this is minus of minus becomes plus. I'll write the j forward. So it means it is an imaginary term. So it is JIM e power minus j beta r, and we have cos of pi by 2 cos theta divided by 2 pi r and 1 sin theta divided by 2 pi r sin theta. Now this is a vector quantity. We will find the magnitude alone. So how do you find the magnitude alone? So this is going to be modulus of h phi is equal to. So what is modulus of j? So j means there is no real part. It is 0 plus j1. So this is going to be root of real part the whole square plus imaginary part the whole square. So root of 1 square becomes 1. Similarly, modulus of e power minus j beta r is mod of cos beta r minus j sin beta r. So this is root of the cos square beta r term plus sin square beta r term, which is again 1. So this term modulus also becomes 1, and for this term also it becomes 1. So what is the magnitude value? It is Im divided by 2 pi r cos of pi by 2 cos theta divided by sin theta. This is the magnetic field of your half wave dipole, and the unit is amperes per meter square. So using the vector magnetic potential found in the previous step, we have calculated the magnetic field component of your half wave dipole. Next, I am going to find the electric field component. So we can actually relate the magnetic field and the electric field component by using the relationship the intrinsic impedance is equal to E theta by h phi, and for free space the intrinsic impedance has a value of 120 pi or 377 ohms. We can take it the other way. So the impedance of free space is 120 pi or 377 ohms, and using the already found value of h phi we will try to calculate the E theta value. So we can therefore write E theta is equal to eta into h phi, which is nothing but 120 pi into the magnitude of h phi. So we can substitute the value of h phi here. Let me scroll down. So this is going to become 120 pi into, we know h phi is Im divided by 2 pi r into cos of pi by 2 cos theta divided by sin theta. So we can cancel out this pi and pi, 2 ones are, 2 60s are. So therefore, what are we getting the electric field component to be? I am getting E theta as the magnitude of electric field is 60 Im divided by r cos of pi by 2 cos theta divided by sin theta, and the unit is volt per meter for electric field. So this is the value of the electric field intensity that we have found using the magnetic field intensity. The last part of the derivation is finding the power radiated and radiation resistance. So next let us calculate the power radiated from the half wave dipole. So we can write the power radiated formula as double integration the average power density over the surface, because we know that we consider spherical coordinate system, it is not a single dimensional quantity, it involves two angles, theta and phi. So that is why we have two integrations here. And the average power is given by half of the real part of E theta into H phi conjugate. So using this, we will first find what is S average, and from that we will try to calculate the value of the power radiated. So we can write this as 1 by 2 into real part of, we know that eta is equal to E theta by H phi. So from this, what is E theta? We can write E theta is equal to eta into H phi. So I'm going to write this as eta into H phi into H phi conjugate. So what is A into A star? We know it is A square. So this will become eta by 2 into modulus of H phi the whole square. This is going to be your average power density. So this is nothing but the average power density. Now we will calculate, we will substitute this H phi value here. So average power density becomes, so this average power density becomes eta by 2. It is H phi square. So we need to take square of the components. So it is Im square divided by 4 pi square r square and angle cos of pi by 2 cos theta divided by sin theta the whole square. So this is your average power density. Using this, we will calculate the power radiated. So substitute this S average in the equation for power radiated. So this is going to become power radiated is equal to double integration, and the integration involves two angles. One is phi, which varies from 0 to 2 pi, and theta varies from 0 to pi for a spherical coordinate system, and it is S average. So eta by 2 Im square divided by 4 pi square r square into cos of pi by 2 cos theta divided by sin theta the whole square. And since this is a spherical coordinate system, ds is given by r square sin theta d theta d phi. So into r square sin theta d theta into d phi. So let us substitute all the values and find the power radiated. So I'll take out the quantities that are not involved in the integration outside. So this becomes eta by 2 Im square divided by 4 pi square r square. What other terms can we take outside? We can take this r square also outside. So the balance terms are 0 to 2 pi, which is phi. Now see what are the terms that involve phi here. It is just d phi alone. So it is integration of d phi. And theta is equal to 0 to pi. What are the terms involving theta? So it is this term. So it is cos square pi by 2 of cos theta divided by sin square theta. Multiplying the square inside, so it is cos square of this particular angle divided by sin square theta into sin theta d theta. So we can cancel out one sin theta term here. Now simplifying further, this will become power radiated is equal to eta Im square. 2 4s will become 8 pi square r square. Maybe we can cancel out the r square also. So let me neglect the term here. So divided by 8 pi square into integration of this gives you phi, and from 0 to 2 pi the value will be 2 pi for us, into integration of 0 to pi. We have the term cos square of pi by 2 cos theta divided by sin theta d theta, because we cancelled one sin theta term in the numerator and the denominator. So balance we have one sin theta that is present. Now if you evaluate this integral value, we won't evaluate this integral. This is a special type of integral that involves cos theta and sin theta values. And we can analyze this by various methods, like we can use the normal integration to solve this. We can substitute cos square theta formula and solve this, or we can use the trapezoidal rule also. On evaluating, this integration has a value of 1.219. So let us directly substitute this value. So therefore it becomes eta Im square divided by, so I can cancel this, 2 ones are 2 fours are, 1 pi will cancel, divided by 4 pi into 1.219. And eta value we know it is 120 pi for free space, so it is 120 pi Im square divided by 4 pi into 1.219. So pi gets cancelled, 4 ones are 4 30s are. So when you actually find out the power radiated, the value is 36.57 Im square. This is the power radiated from a half wave dipole antenna. Now to end up the derivation, we need to prove that the radiation resistance of a half wave dipole is 73 ohms. That is the main part. Because what we started is that the radiation resistance is 73 ohm and it is easy to match the transmission line and the half wave dipole. So we need to calculate and show that the radiation resistance is 73 ohm. So how to calculate the radiation resistance? We know that the formula for power radiated is I square into R. So power radiated will be the radiation resistance RR and the RMS value for current. So from this we can find the radiation resistance RR formula as the power radiated by this I square RMS. And we know the maximum current in our circuit, and we can find that IRMS is the maximum current divided by root 2. So we will substitute this here. So this becomes PR divided by Im by root 2 the whole square. So therefore radiation resistance is equal to PR divided by Im square by 2. Reciprocating this term, this becomes 2 PR divided by Im square. We have already found PR in the previous step, so substitute the power radiated value here, and therefore the radiation resistance becomes 2 into what is power radiated? It is 36.57 Im square divided by Im square here. So if I cancel out this Im square and Im square, we are getting the radiation resistance to be approximately equal to 73 ohm. 2 into 36.57 gives you 72 point something, which is nothing but 73 ohm. So therefore, since your half wave dipole has a radiation resistance of 73 ohms, matching the half wave dipole with the transmission line is much easier, and hence matching is made almost perfectly. We can say that there is maximum radiation and the reflections are minimized. So this is the design of a half wave dipole antenna. Thank you.